SwayamPrabha. Digital India. Educated India.
Okay, so welcome back. So where we stopped last time was the mean mechanical energy equation, and we were discussing that because we realized that although we did incorporate the definition of turbulent velocities into the continuity, momentum and energy equations, we would still probably need more information about a turbulent flow. And a mean mechanical energy equation, which is essentially proposed by Prandtl, is something that we should be looking at. So I wrote it down last time for you. Okay, and now so look at that equation, right? Now an integral form of that is usually used for solving laminar flow, right? And we subtract that equation from an instantaneous version, and what we get is this, and what I'm going to write out right now, and then look at each term, and it has some, it will give us a little more information that we're looking for about a turbulent flow. Okay, so the equation that I'm looking at is this. Right. So essentially I'm taking time averages, okay? Okay. Okay, and again we take a time average of that term. Okay. Okay. Okay, and again we take a time average of that. Okay, so now essentially we have this term, so I'm going to write them out. Okay, so this term, this term let's just call that as 1, okay. Let's call this term as 2, okay. This as 3, and as 4. Okay, and of course Q square is equal to right. So essentially this is the turbulent KE. Turbulent KE. Okay. Let us also label the first part. Okay. Let's call that as O. Okay. Now these terms mean something. Okay, and that is important. Now these terms mean something, and that is important. Okay, so let me write down what do these mean. Okay, so if you look at this, what does the first term mean, right? So Q square is the turbulent KE, right? So could I just write this O? Could I say that this actually means rate of change of a mean turbulent KE, the time average? When I say mean, I basically mean the time average, right? Okay, so this is rate of change of time averaged or mean turbulent K. So basically half rho V square, right? So yeah, I kind of wrote here turbulent KE. So yeah, so essentially this has to be half this term here, Q square. So I multiply that half into rho, and then I get the turbulent K. So I'm going to just write, essentially this is Q square is the square of the turbulent quantities of the fluctuating components of the velocity squares. Okay, all right. So the next one is 1. Okay, and what is that? Is the convective diffusion of turbulent energy. Okay, so this is convective del xi, right, diffusion of turbulent energy, right. So of course you, on one side you have the half rho V square, which is the KE, and then you also have the fluctuating pressure component, which is going to, you know, give us the changes in the energy due to the pressures, right. And all of that is happening over as the fluid is moving with a velocity, which is the fluctuating part, so which is the UI, right. And so we look at that change in the velocity over space, right, which is x. So hence convective diffusion of turbulent kinetic energy, sorry, turbulent energy, right. Okay, so then right, what is this? So this is, we shall discuss this a little later on. So as of now, I'm going to just write this out. Okay, this is essentially production of it is a production of turbulent energy. Okay, I think it's important to address at this point of time that where does it come from? You know, you have a flow which is laminar, right, and then it becomes turbulent. So where does this energy come from, which makes it turbulent, right? So production of turbulent energy. Okay. So, work done by turbulent viscous forces. So, we have a viscosity component there. Okay. So, this one essentially is work done by turbulent viscous stresses. Okay. And finally, the fourth term, turbulent viscous dissipation. Okay. So, we have an equation here, right. So, that is it. So, basically this is an equation, this is the mechanical energy, mean mechanical energy equation, right, and we use an instantaneous version as well. So, basically we are saying on the left hand side is what is this? So, this is a rate of change of mean turbulent kinetic energy, right. So, previously we have looked at dV dt and things like that, right. We have looked at the rate of change, basically the acceleration of a fluid flow, right, total acceleration of a fluid flow, and we had two terms and we understood that. Now, in this case, however, we have the rate of change of mean, right, mean turbulent kinetic energy, right. So, that is essentially is given by four, the change is given by four of these quantities here, right. The first one being there is a convective diffusion going on here of turbulent energy, there is a production of turbulent energy, there is a work done by turbulent viscous forces, and there is also turbulent dissipation, right. So, now, so that is that really. Now, the point is that, okay, so if there is a turbulent flow, right, and therefore, there is going to be a change in the kinetic energy, it's a lot of chaotic random movement. So, there's going to be a lot of change in the turbulent kinetic energy, and every time I study these, right, I am going to have all of these things spread out over the entire turbulent flow field, which is a convective diffusion, production, work done by the viscous forces, and turbulent dissipation as well, right. Is that so? Or the 1, 2, 3 and 4 may or may not happen all the time. What will that depend on? Okay. Will it depend, now if you have very large regions, sort of comparatively larger regions of chaotic movement, do we have all of these or some of these dominate? And if you have a very small region of turbulence, right, so then do we have a lot of convective diffusion there? Do you have a lot of production, work done, viscous dissipation? How is energy being transferred? Okay. So, I think those are questions, something that we should be asking at this point of time, and hopefully as we go along some of those questions are going to be answered. Okay. Now that we sort of got a hang of basic equations in place, we will start with real examples and study them and understand them, right. So, what we have done so far is looked at the basic equations that one will be using, which is the governing equations, and continuity, momentum, energy. We looked at that. We incorporated the definition of turbulence by using the mean component of velocity and the fluctuating component into these equations, and we saw how they look like. We did get some information, but we thought that a lot of a physical feel for the flow is kind of missing. So, we thought we should get a little more information. Hence, we are now talking about this mean mechanical energy equation, right, and where it is basically giving me a relationship for the rate of change of mean turbulent kinetic energy, right. So, which is this. and I get that, and all these 4 terms that I have here have a certain physical meaning to them, right. So, we think that we have some more information here, and as we go along we will see how this fares and what's the best, I mean, do we really understand these things, and what is the way that these things, the physical nature will actually show up, because of the way I have written out this equation. Okay. So, for now, so we have looked at the equations, all right. So, we will take specific cases and we will study them. Okay. Now, one of the, so let me look at, so what we will start actually from the next class is essentially something called a round jet. Okay. What is a round jet? So, we shall just get to that in a bit. So, let us go to a little presentation that I have made, and okay. Now, this is the first thing that we are going to start studying. Okay. Now, these turbulent round jets. Now, what are these turbulent round jets, and where do you see them? Right. So, I have just put together a little presentation, and you should be able to, look on the internet, and of course, you should look around yourself. It's all everywhere. Get out of the classroom and look for signs everywhere, essentially. So, examples. This is you must be seeing this, seen this at some point in your life. Is essentially wastewater discharge, right, into the so you have the wastewater examples of wastewater discharge here, yeah, from pipes into oceans and seas, rivers, what have you. Okay, and you can see here that we are looking at pipes, right. We are looking at, so I am calling this a round jet, right. So, clearly all the pipes are round. Okay, why am I calling this a jet? Well, there is fluid, right, which was moving from through this pipe, right, through these pipes, and these pipes have a certain diameter, right. So, at one point when it comes here, so then suddenly that the diameter drastically changes. That is one thing, and also the atmosphere in which it was moving here, the conditions in which the water or the fluid rather was moving through these pipes, it changes, and it could be velocity, it could be temperature, it could also be the amount of contamination, right, because this is all dirty and wastewater which is being discharged into the rivers or oceans, right. Now, I'd like you to sort of look at these these structures, okay, and you can see this, right. Now, what you should be able to do is take a glass of water, take your time and pour it and see how that looks like, right. Open your tap and look at the water flowing, and you should also look at the sides, right, right near where the little pipe of water is flowing down. You should also look at the sides a little bit as to how it is behaving, right. And then if you look at the way the water is there a reason why the water is going to flow like this, right, the flow conditions being so and so forth. So, in the sense that you can make a see here, this is a calm, probably the ocean surface or the river surface right here, and then you see this water moving, right, and there are little waves here in the ocean, etc. But then this is drastically different from what's going on in here in terms of the flow structures, right. So, clearly obviously this is turbulent flow, and this is something called a jet. So, jet because it is coming out through an orifice, and into, like I said, the diameter really changes very, very drastically. So, it comes out from a small orifice like that into completely where there is no boundary at all. So, that is going to cause a jet, and that is what this jet is all about. Okay. So, this is one of the practical examples of where you can find actually a turbulent round jet. Okay. All right. So, going to the next one. Okay, there you go. All right. So, we have this another example of this, and these are essentially industrial smokestacks, right? So as you can see here, right, as you can see here, look at the flow structures going on here, right? Again, smoke is coming out of, small orifices into the open atmosphere, and you can see the type of flow here. You should be able to, like I think I spoke about this, you should be able to look at, the agarbatti smoke, right? And it should give you, and if you sit at a little dark, and if you see the agarbatti smoke, is just turbulent flow right, at your fingertips, really, the easiest form that you can look at. So if you see, these are several examples of that. This is coming out from a power plant, okay. So these are examples that you can see, and you can see these flow structures. These are quite, interesting, right? And one needs to wonder that why is it that when such kind of flow is coming out of, say, orifices like that, why does it have to behave like this? Why does it have so many? It seems like the structure is complicated, and how. And also one needs to wonder as to, these are all fluid particles, and how are these fluid particles behaving in a flow which looks like this, right? Okay, so that's another example. Okay, all right. So now those are some practical examples that I've showed you, right? And I think what one should be doing is essentially looking for these around you all the time and see turbulence around you, right? So when I say what is turbulence, it's not a definition from the book that you need to be giving, but really understanding what that means. And I'm not claiming I understand all of that either, but what you really need to do is look around you. It's nature, right? It's really nature. It's everything is in nature, and we are basically trying to understand that. Okay, so obviously you see the need to study turbulence and such kind of things, and hence researchers have gone into depth about studying these things, right? So hence I have a couple of laboratory examples out here. So this so what you see on the left hand side here is essentially an experimental example. Experiments were done in a laboratory, and what you see on the right hand side is essentially CFD, computational fluid dynamics, and you must be familiar with something like this. So the experiments that you see on the left hand side is for a low speed subsonic flow, while the CFD on the right hand side is for a supersonic flow. Okay, so if you look here, I've given you the reference from where this is taken, right? And you should be able to look this up. Now, if you look at this, what is going on here? So there is a jet which is coming out. Okay, it is a jet which is coming out, and the researchers are essentially what we are looking at is, if you look at the jet, it is like that. Okay, now this is a flow visualization which using a laser induced fluorescence, right? So and this is the side view of that. Okay, the Reynolds number based on dia, so this along this axis will be your dia, so Reynolds number is around 5,500. Okay, and this region, where is the arrow is, that's the region that we are looking at. Okay, so I can so this is the region that we are looking at. Okay, where okay, that's the region that we are looking at, which is essentially shown in the these two diagrams, this and this. Okay, two views of that. Now this region is at x by d is 3.5. So what is x? So x is along this, right? And d is along this. So essentially the length, the x is so x would probably start from around here. I think the flow is starting from here. I think from here. Okay, so if you see x by d, so the axis system will probably be located somewhere over here, right? So essentially 3 times the diameter. Okay, so x, this is 3 times the diameter here. Okay, so 3.5 times rather. So this is the location that we are looking at. Okay, so again, laser-induced fluorescence of cross sections. So if you see, this is the kind of stuff that you get to see. Okay, on this side they call it a ring, and this side they call it a braid. Well, if you look at this, what I am looking at personally is, look at these, these are pairs of vortices. They seem to be pairs of vortices, right? And there are several formations inside of this thing, right? So you see the flow structure. I mean, compare this with, say, the surface of an ocean. Compare this with flowing through a pipe. Compare this with flow. Yeah, I mean, basically, you're pouring a glass of water, and compare that with this, right? So now, if I were to sort of go back to the pictures of the jets that we were looking at, let's do that, shall we? Okay. Yeah. So if we were to sort of go back, right? So something like this, right? When you have something like this, okay, if you see the structures here, right? So we are looking at it, from the side, etc. But so the point is, how are these particles behaving at every location or every section and things like that. So that's exactly what we're trying to look at, right? So therefore, so again, so when I come here, right, I look at this and I see these flow structures, right? So now one thing is to sort of notice this. This is a flow visualization. So you just set up an experiment and you see this and you look at this, right? And again, if you look at, say, another view of that, right? They're calling that a braid. Well, it's so again you see some different structures over here, right? So you're looking at 2 different cross sections, and you see these kind of formations there, right? Which is very interesting, right? Because this is very different from if some things were laminar, right? So if just compare this with something which is a laminar flow, and then this is a turbulent flow, right? And it's, as such, it seems pretty simple. You have a slightly smaller dia of a pipe through which a fluid is moving, and then it comes out with a certain velocity, right? And it just expands, fine, right? But then you seem to have very complex flow structures. These are all flow structures. And how do we get these? The flow particles, they're moving in such random ways, right, that they form these things. Do you realize that? Right? So if you have a laminar flow, all the fluid particles are essentially moving, in the same direction, right? That's why we have nice little laminar flow and same direction, or at least they are moving in, if I'm able to draw some specific lines, or if I'm able to track, the path of these particles, at least, fairly well, then at least it's something that I can understand. But here things seem to be very complex and very complicated, and this is happening because the fluid particles are moving in such ways that they're forming, say, the ring or the braid, right? So now, while having looked at this, setting up the experiment, taking pictures and looking at this is one thing. Another thing is we looked at the basic fundamental equations of motion: continuity, momentum, and energy. Now, when you look at these, irrespective of any sort of complex movements that these fluid particles are doing, they still should be satisfying the basic fundamental equations of motion, right? And mass, momentum, and energy have to be conserved, even if they're making several motions which are hardly even there in a laminar flow, right? So they are making so many movements, but still the fundamental equations of motion will have to be satisfied. Okay. So, and then we said that, so therefore what we see is now another question is important to notice here is that at this location, right, we're talking about, no, there was Okay, so this location, right? So this location we have these two, views. So these are the two, formations, so to speak. Now, what happens if instead of x by d is equal to 3.5, I move further downstream? Will I see the same, views there as well, or will I, when I look at this, say at this particular section, or this particular section, will I see the same thing? For one, if I move from 3.5d to say 4d, right, or say 5d or 6d, one thing that you can see that there is a spread. This thing is spreading, right. So, dia itself is changing, dia of the spread is changing, right. So, when we say RE dia is basically dia of the orifice. So, I think it will be somewhere over here, okay. It is of the orifice, right. Now, so that is one thing, right. So, these are the kind of things we will need to sort of look at and study when we look at when we study the round jet, right. Another thing is we spoke about the fundamental equations of motion. We also got in the mean mechanical energy equation, hoping that we should get some more understanding of the fluid flow. So now another question is, you have these sort of formations here and here and here, so and so forth. Now, so these fluid particles are constantly moving, right. So, if I have fluid particles here, I have fluid particles here which are spread out. So, that means there is motion across that plane, right, and some places it is pretty strong, some places it is pretty thinned out, right, which means there are lesser particles here. So, more particles are moving in this here, right. So, therefore, there is random motion, right, along the axis of flow as well as across it, right, as we move in space as well as in time, right. So, therefore, if particles are moved, so all the particles, if a particle was moving in a certain direction, a certain velocity, that is probably changing as I move along, right, as I move to another location in this flow field, right. So, therefore, so in that case there is going to be an exchange of energy, right. So, therefore, we have these four terms, which from mean mechanical energy. How do those play up here, right. So, if a particle is say moving from this location to this location, what kind of energy changes is that going to have, and how is that equation going to help me to figure that out? If the particle was here and now it is here, where exactly is it located in the direction, perpendicular distance, in the perpendicular direction, right. So, these are questions hopefully, and if it comes from say here, the particle says here, right, and then it goes into a very small region here, it goes to a very large region here, or it is located in a very small region, say somewhere over here, right. So, how is that energy change going to be affected if the particle is located in a very small little place here compared to a large mass of turbulent flow? I think these are the type of questions that we should be asking and trying to understand, right. So, those are the kind of things we will try to answer when we start to do that, which is essentially next class. Now, like I said, this is an experiment, right, and so people basically set it up and then they look at these pictures, and then of course, I'm just showing you the pictures. There is a math and the calculations, etc., which you look at, right. Now, the point is, we studied all these equations. Now, what about that? Can we actually take that and recreate or study, analyze a turbulent fluid flow? Can we do that? Well, I guess we can, because that's exactly what this is all about. It is essentially the continuous stage of the free round jet, right. The coloring here, right, is so contour of velocities, contour of the velocities in logarithmic color scale, right. So, you have several color schemes here, right? And this is essentially done so to basically what you're trying to predict is how the velocities will behave in a jet which is like this, right? And this is from CFD. How wonderful is that? Okay. Now again, this is the reference is given here, okay, and what you should be doing at this point of time is really looking at, you know, examples around yourself, right? And I have examples of I've given you the links here, so 3 videos to show what you know turbulent flow can be look like. So let's go and look at that first, okay. So let us look at these videos first, okay, and this is going to be interesting, okay. So well, these are examples which are all there, which is, you know, you can see the values, etc., right? So you can look at that. These things may not make a lot of you know, sense at this point of time, but hopefully as we learn, you go and look at more of these things, and you know, you should be able to understand. I hopefully things will start making a little more meaning. So first off, if you see this picture here, right? If you see this picture here, isn't it quite wonderful that you've actually recreated the exact type of behavior or how the fluid looks like when it is leaving, you know, as from the smoke towers, as I had shown you earlier, right, in the real life pictures, or for that matter, the dirty water that is being discharged, right. So we've created that kind of a flow field exactly as that, right, so that we can study this. So let me play this for you, okay, let me play this for you, and let us see what this sort of how, and I think it's important to note, you know, note the colors, and note that this pink color or whatever is really disappearing, you know, it's not there at all after a certain while, right. The movements, etc., etc. Okay. Okay. So let's sort of do that again. Okay. Let's look at that. What is important to note is how this is, and look at the edges as well, right? How it fades out a little bit. So there seems to be, I don't know if you can you know, concentrate on this. There is a certain, you know, part in the middle, right, which seems to be, which kind of just remains as is, and then the side starts sort of, you know, blurring out a little bit. But there is one part in the middle which seems to remain, you know, pretty much in its place. Actually, that is really the core of the jet, as they say. Okay. Now, this was the core of the jet. So this was really, which was right next, you know, right next to. This is right next to where the fluid is being discharged, right. Now if I go, so I look at this, now what if I go really farther down, right? If I go farther down, then what happens, right? Okay. So that's the kind of thing that we have here, okay. So this is a picture that we have which is farther down, right, which is a farther down, and if you see, this is the kind of flow structure it kind of looks like, right. So what one must be looking at is how things are changing as we move, you know, along with the flow, right. So it seems to be this way, whether, you know, if we move along the direction of the flow, which is bottom up here, okay. And also how it is behaving across it, also how it is behaving across it. Okay, so again finally I have these, I have sort of done this here, but you should be able to look at, several of these videos, etc. A lot of this is available online. Yes, I got these online, so you should be able to look at it and, have fun with it actually, and so it is interesting. Okay, let's look at this video first. So this is actually a turbulent pipe, right? Flow exiting in a co-flow is visualized with isosurfaces of a vortex identification criteria. The structures are colored. So this is important. The structures are colored with a streamwise velocity component. The mean bulk velocity in the pipe is at a Mach number of 0.5, and the Reynolds number based on pipe radius is 7,700. It's around that. Okay, less than all 10,000. Okay, so let us do that. Right, it's quite interesting that we're looking at flow structures, right? We're actually looking at flow structures, and which look like this. It looks like small beans. Okay, so essentially, so that's what. So now, if I were to just sort of go back to this a little bit, so this is the type of flow that we were looking at, and what I showed you is that. Okay, so actually. This is in reality, this is what you have in actual practice, and then if you see this sort of this sort of a formation, or this sort of this picture out here, right? Now this is what is sort of developed in the lab, right? You do that with you set it up in such a way that you will actually have this flame which you're looking at, and this is also generated, which is also, if you see this, right, it is generated using commercial, using basically writing numerical codes, right, and this also looks exactly, or looks similar, looks like the turbulent jets that we are planning to study, right. So therefore, just think about how this is going to be useful. Say you need to figure out as to the efficiency with which these fumes need to be let out, right. So therefore, how do we sit and decide that how much fumes are going to leave in a particular day, or given the number of smoke towers that you have, etc., etc. How are you going to answer that question if a client comes to you, right? So then you, as a fluid dynamicist, I guess, right, will have to sit and do some kind of tests to figure that out. Said, okay, how much fuel are you burning? How much fuel do you have? Okay, and what is the size of the smokes jets? Okay, this much. Fine, great. So then this is the amount of smoke that you will get. This is the amount of time that is going to be in the atmosphere around your factory, and then as we go farther down, the contamination is going to be this much. So those are the type of questions you might need to answer when you are really looking to study something like this. Okay, so now our task is really cut out, where what we need to do is really get to the design table and figure out, put a certain axis here, call this X, and D, what have you, and really give a picture, and try and figure this out, study this inside and out, right, and to get information as to what, how this will pan out. So another thing, I also said this is a free jet because there could be something else. So I said free jet. Now these are all free jets that you looked at, even the examples that you looked at, right. Okay, so now if you look at this, so if you look at this structure and if you look at this structure, so it's interesting, right? So this is also in all the three pictures here, they actually water, right? But the contaminations is probably different, right? So what will be interesting is to figure out, right, that say given in an hour, right, how much of this water, how much of this dirty water is going to spread. Given in 1 hour, you're placing so much of dirty water, wastewater into the river. So how exactly is this going to move, and where is this going to land up, right? So that's the type of questions so we will need to figure out, and that's the type of questions probably we will try to answer. And again, like I said, what exactly are we looking to study here? I understand this is a round jet and all of that, and these pictures are exactly similar to what we are studying there. But then, how do I figure out? What exactly is it that I'm trying to look at when I say I want to study the round jet? What exactly do you want to study, right? Like I said, if I have a fluid particle which is right here compared to a fluid particle which is here, right? And if their energies are different, then how are they being, how are they being dissipated, or how are they being interchanged, right? The energy has to go somewhere. What is going on there, right? So these are the type of questions we will try to answer. So especially this kind of in fluid mechanics is very common, instead of, where you take specific examples and study them, because the structures, for example, what you have here in a water discharge, these structures are very different, right, compared to, for example, a boundary layer. You have a airplane wing and you have a boundary layer over that. Now that could also be turbulent, sure, but I'm talking about a laminar boundary layer. So that the behavior is going to be very, very different. So in the sense that, so we have basically class of problems, right, because for that particular class of problems we have a set of equations, right, which we use to study. Right. So in this case, turbulent round jet is almost, it's a topic. It has its practical uses, and we are basically going to go on a journey figuring out, putting math, into this physical phenomenon, right, which is what we shall sort of start in the next class, right, and I shall drop the whole picture, etc., etc. So if I'll just stop by simply looking at the pictures one time. So you have basically these are jets, as you can see, and for example, if you look at this, if you look at this picture, fumes which are coming out of turbulent jet, right? Now you see there are fluid particles which are located very close to the jet, right? So to this orifice, they all seem to be mixing. These things are moving. They are not just moving away from it, towards each other and things like that, right? So if for example, you have two of these. So if you have a particle here, it will be in this jet, or is it move away slightly? And what is the distance, sort of, will be its maximum spread? in perpendicular to its axis. Thing that we are studying here seems to be attached almost, and then it kind of spreads out. Okay, so I think what we will start doing math of turbulence next class, and stop here, and that's in the next one. Thank you.